For the unit thermodynamics, in previous lecture we discussed various factors influencing enthalpy of reaction, enthalpy of formation or heat of formation, and enthalpy of combustion or heat of combustion. In continuation, today we will discuss various applications of enthalpy of combustion, calorific values of food and fuels, enthalpy of solution or heat of solution, and enthalpy of neutralization or heat of neutralization. Enthalpy of combustion has various applications in thermochemistry. We can calculate calorific values or fuel values of various fuels with the help of enthalpy of combustion. Energy is required for the working of all machines. Petroleum, natural gas, etc. are used as energy sources for man-made machines, and the different food products which we eat are used as the energy sources for our body. These substances undergo oxidation or combustion to produce energy and hence are called fuel. The grading of different food articles and different fuels is done on the basis of their calorific value. The calorific value or the fuel value is the amount of heat produced per gram of the fuel combusted. For example, when methane burns, 890.3 kilojoule per mole of energy is released. You can see that in this equation. CH4 gaseous plus 2O2 gaseous gives you CO2 gaseous plus 2H2O liquid. Here delta H of the reaction is equal to minus 890.3 kilojoule. Enthalpy of reaction for this reaction is also enthalpy of combustion for methane. As when 1 mole of methane burns, 890.3 kilojoule of heat is produced. So, the amount of heat produced when 1 gram of methane will burn will be equal to 890.3 divided by 16, which is equal to 55.6 kilojoules per gram. Hence, calorific value of methane is 55.6 kilojoules per gram. In this table, you can have a look on calorific values of different foods and fuels. Various fuels listed in this table, hydrogen have the highest calorific value. But hydrogen is generally not used as a domestic or industrial fuel because of some technical problems. On examination of calorific values of different food items, you can see that fats and carbohydrates are the main sources of energy for our body. Here is an example to calculate the fuel efficiency or calorific value of the fuel. The heats of combustion of CH4 and C4H10 are minus 890.3 kilojoule per mole and minus 2878.7 kilojoules per mole respectively. Which of the two has greater efficiency as fuel per gram? As molar mass of methane is 16, hence heat produced per gram of methane will be equal to 890.3 upon 16, which is equal to minus 55.6 kilojoules per gram, and molar mass of butane is 58. Hence, heat produced per gram of butane will be equal to 2878.7 divided by 58, which is equal to minus 49.63 kilojoule. Hence, fuel efficiency of butane will be equal to 49.63 kilojoules per gram. Therefore, methane has greater fuel efficiency than butane. There is another example to calculate the fuel efficiency per centimeter cube of the fuel. An intimate mixture of ferric oxide and aluminium is used as solid fuel in rockets. Calculate the fuel value per centimeter cube of the mixture. Heats of formation and densities are given as: heat of formation for Al2O3 is equal to minus 399 kilocalories per mole. Heat of formation for Fe2O3 is equal to minus 199 kilocalories per mole. Density of Fe2O3 is equal to 5.2 grams per centimeter cube, and density of aluminium is equal to 2.7 grams per centimeter cube. Now, the required equation for the calculation of this example is 2 aluminium plus Fe2O3 giving Al2O3 plus 2 Fe. Now delta H for this reaction is not given. So delta H of the reaction will be equal to delta H products minus delta H of reactants, which is equal to delta H formation for Al2O3 plus 2 into delta H formation of Fe minus 2 into delta H formation of aluminium plus delta H formation of Fe2O3. This will be equal to minus 399 plus 2 into 0 minus 2 into 0 plus minus 199, which is equal to minus 399 plus 199 equal to minus 200 kilocalories. Now atomic mass of aluminium is equal to 27 and molecular mass of Fe2O3 is equal to 160. Hence, volume of reactants which you can calculate from the data given for densities will be equal to 160 upon 5.2 plus 2 into 27 upon 2.7. This is equal to 50.77 centimeter cube. Hence, fuel value per centimeter cube will be equal to 200 divided by 50.77, which is equal to 3.92 kilocalories per centimeter cube. Enthalpy of combustion has another application, that enthalpy of formation of various substances which cannot be calculated directly can be calculated with the help of data given for the enthalpy of combustion. Here is an example to understand this fact. When 2 moles of C2H6 are completely burnt, 3129 kilojoules of heat is liberated. Calculate the heat of formation of C2H6. Delta H formation for carbon dioxide and H2O are minus 395 kilojoules and minus 286 kilojoules respectively. Now the equation for the combustion of C2H6 will be 2 C2H6 plus 7 O2 giving you 4 CO2 plus 6 H2O. Delta H for this reaction is given to be equal to minus 3129 kilojoule. Now delta H for the reaction will be equal to delta H for the products minus delta H for the reactants. Hence, delta H will be equal to 4 multiplied by delta H formation of carbon dioxide plus 6 multiplied by delta H formation for H2O minus 2 multiplied by delta H formation of C2H6 plus 7 multiplied by delta H formation for O2. As delta H reaction is minus 3129, therefore minus 3129 will be equal to 4 multiplied by minus 395 plus 6 multiplied by minus 286 minus 2 multiplied by delta H formation for C2H6 plus 7 multiplied by 0, or we can say that 2 multiplied by delta H formation for C2H6 will be equal to minus 167, or delta H formation for C2H6 will be equal to minus 167 divided by 2 equal to minus 83.5 kilojoules. The calorific value or fuel value can also be calculated per ml or per centimeter cube or per meter cube of the fuel. Here is an example to understand that calculation. The standard heats of formation of CH4 gaseous, CO2 gaseous and H2O gaseous are minus 76.2, minus 398.8 and minus 241.6 kilojoules per mole respectively. Calculate the amount of heat evolved by burning 1 meter cube of methane measured under normal conditions, that is at NTP. The required equation for the combustion of methane will be CH4 plus 2O2 giving you CO2 plus 2H2O. Here delta H for the equation is not given. Delta H for reaction will be equal to delta H products minus delta H reactants. Hence, delta H of the reaction will be equal to delta H formation for carbon dioxide plus 2 into delta H formation of H2O minus delta H formation for methane minus 2 into delta H formation of oxygen. Hence, delta H will be equal to minus 398.8 minus 2 into 241.6 minus 76.2 minus 2 into 0, which will be equal to minus 805.8 kilojoules per mole. Now, heat evolved by burning 22.4 liters, that is 1 mole of methane at NTP, will be equal to minus 805.8 kilojoules. So, heat evolved by burning 1000 liters, that is 1 meter cube of methane, will be equal to minus 805.8 divided by 22.4 multiplied by 1000, which is equal to minus 35973.2 kilojoules. Now we will discuss the heat of solution or enthalpy of solution. The enthalpy of solution is the amount of heat produced when 1 mole of solute is dissolved in solvent such that further dilution will not produce any enthalpy change. Here are some examples for the heat of solutions of different substances. The heat of solution for H2SO4 is minus 20.2 kilocalories. It means dissolution of H2SO4 is an exothermic process. The heat of solution for potassium chloride is equal to plus 4.4 kilocalories. This shows that dissolution process of potassium chloride is endothermic process. The heat of solution of KOH is minus 13.3 kilocalories, which shows that dissolution of KOH is an exothermic process. Generally, dissolution of substances in a solvent is a disintegration process. This process needs energy. Hence, energy is absorbed during the separation of ions or during the disintegration of solute. But sometimes hydration also takes place during dissolution. During hydration, energy or heat is liberated or evolved. Hence, in dissolution process, energy can either be absorbed or evolved. Sometimes it happens that energy of ionization is nearly equal to the energy of hydration. In those dissolution processes, very less amount of energy is absorbed or evolved during the dissolution of the substance. For example, heat of solution for sodium chloride is very less because the heat of ionization and heat of hydration are nearly equal for sodium chloride. With the help of enthalpy of solution, we can calculate the enthalpy of formation of ions in solution. Here is an example to understand that. The enthalpy of dilute solution of potassium chloride at 25 degrees Celsius is 17.19 kilojoule, and the standard enthalpy of formation of potassium chloride solid is minus 435.89 kilojoules. If delta H of Cl minus aqueous is equal to minus 163.44 kilojoules, calculate the standard enthalpy of formation of K plus aqueous ion. Now, the reaction required for this dissolution process will be KCl solid plus aqueous, giving you KCl aqueous. KCl aqueous means K plus aqueous plus Cl minus aqueous because KCl is strong electrolyte. Now, delta H for this process is given in the problem, which is equal to 17.19 kilojoules. Now, delta H for this reaction will be equal to delta H of K plus aqueous plus delta H of Cl minus aqueous minus delta H of KCl solid. Hence, 17.19 will be equal to delta H of K plus aqueous minus 163.44 minus 435.89 kilojoules. Therefore, delta H for K plus aqueous will be equal to minus 251.26 kilojoules. Enthalpy of neutralization is another very important type of enthalpy which must be studied in thermochemistry. Enthalpy of neutralization is the amount of heat produced when 1 gram equivalent of an acid is completely neutralized with 1 gram equivalent of a base in dilute solution. For example, if 1 gram equivalent of strong acid will get completely neutralized with 1 gram equivalent of base, salt and water will be produced and 13.7 kilocalories of heat will be liberated, that is delta H for this reaction will be equal to minus 13.7 kilocalories. Aqueous HNO3 plus aqueous NaOH giving you NaNO3 aqueous plus H2O. Delta H for this reaction is also equal to minus 13.7 kilocalories. If we take another example, that is HCl aqueous plus NaOH aqueous giving you NaCl aqueous plus H2O liquid, delta H for the reaction here also is equal to minus 13.7 kilocalories, or half H2SO4 aqueous plus NaOH aqueous giving you half Na2SO4 aqueous plus H2O liquid, delta H here also is equal to minus 13.7 kilocalories. It is observed that heat of neutralization for strong acids and strong bases is equal to minus 13.7 kilocalories no matter what acid or base is used. This constant value can be explained on the basis of ionization theory. Strong acids and strong bases are strong electrolytes and exist as ion in dilute solution. For example, if we take a strong acid Ha, it will exist in dilute solution as H plus A minus, and if we take a strong base BOH, it will exist in dilute solution as B plus OH minus. Hence, if this strong acid and strong base are mixed in dilute solution, the reaction which will take place will be H plus A minus plus B plus OH minus giving you B plus A minus plus H2O, and delta H of reaction is equal to minus 13.7 kilocalories. Cancelling the common ions on both sides of the equation, we will get H plus OH minus giving you H2O with delta H equal to minus 13.7 kilocalories. Thus, the heat of neutralization for strong acid and strong base is the heat for the combination of H plus and OH minus ions to form the H2O liquid. This reaction will remain same in all the strong acids and strong bases, whatever the acid or base may be. But in case of weak acids or weak bases, some heat will be used in the ionization of acid or base. Hence, if weak acid and strong base, or strong acid and weak base, or weak acid and weak base are mixed, then observed heat of neutralization is less than 13.7 kilocalories. Let us have a look on some examples. If HCl aqueous plus ammonium hydroxide aqueous reacts to give ammonium chloride aqueous plus H2O, delta H of reaction will be equal to minus 12.3 kilocalories. If HCN aqueous, which is a weak acid, plus NaOH aqueous reacts to give NaCN aqueous plus H2O, delta H of reaction is again equal to minus 12.3 kilocalories. If CH3COOH aqueous plus NH4OH aqueous reacts to give CH3COONH4 aqueous plus H2O, delta H of reaction will be equal to minus 11.9 kilocalories. We can see that delta H neutralization in all these three cases is less than 13.7 kilocalories. The reason for this lower value is that some of the heat released in the neutralization is also used in the ionization of weak acid or weak base or both. The reaction between ammonium hydroxide and HCl can be shown as ammonium hydroxide will first gets ionized to give ammonium ions plus OH minus ion. Let us take delta H equal to Q for this reaction. Hence, ammonium plus aqueous plus OH minus aqueous plus H plus aqueous plus Cl minus aqueous will give you ammonium aqueous plus Cl minus aqueous plus H2O liquid. The heat liberated in this reaction will be equal to minus 13.7 kilocalories. Therefore, NH4OH plus H plus Cl minus giving you NH4 plus Cl minus plus H2O, the heat of reaction for this reaction is equal to minus 12.3 kilocalories. Therefore, Q minus 13.7 will be equal to minus 12.3, or we can say that Q is equal to 1.4 kilocalories. Hence, 1.4 kilocalories is the amount of heat which will be required in the complete ionization of ammonium hydroxide, and this energy will be subtracted from 13.7 kilocalories. Hence, the observed heat of neutralization will be less than 13.7 kilocalories. Here is an example relating the enthalpy of neutralization of strong acid and weak acid. The enthalpies of neutralization of a strong acid Ha and weaker acid Hb by NaOH are minus 13.7 and minus 12.7 kilocalories per equivalent. When 1 equivalent of NaOH is added to a mixture containing 1 equivalent of Ha and Hb, the enthalpy change was minus 13.5 kilocalories. In what ratio is the base distributed between Ha and Hb? Let X equivalents of Ha and Y equivalents of Hb are taken in the mixture. Then X plus Y will be equal to 1 because the mixture is taken as equal to 1 equivalent. Hence, X into 13.7 plus Y into 12.7 will be equal to 13.5. Now solving equation 1 and 2, we will get X equal to 0.8 and Y equal to 0.2. Therefore, X is to Y equal to 4 is to 1. Heat of neutralization or enthalpy of neutralization can be determined in the laboratory experimentally. The heat of neutralization of an acid or base can be easily determined in the laboratory with the help of polythene or polystyrene bottle. The bottle is fitted with rubber cork through which a thermometer and a stirrer are fitted. 100 ml each of acid and alkali of equal normality are taken in separate bottles. The temperature of each solution is regularly recorded. When both the solutions attain the same temperature, the alkali solution is quickly added to the acid solution. The mixture is stirred and the maximum temperature attained is recorded. Now let the initial temperatures of both the solutions is equal to T1 and the final temperature attained is equal to T2. Then change in temperature will be equal to T2 minus T1. For simplicity, the heat capacity of bottle is neglected as it is very less as compared to the heat capacity of the solution, and the specific heat capacity of the solution is taken to be equal to the heat capacity of the water. Now Q, which is equal to the heat change in the reaction, will be equal to mass of the solution multiplied by specific heat capacity multiplied by delta T. Therefore, Q will be equal to m into S into delta T, which is equal to T2 minus T1. Here Q is the heat evolved by the neutralization. Here the enthalpy of neutralization will be equal to Q upon 100 multiplied by 1000 multiplied by 1 upon X. Here X is the normality of both the solutions. Here is an example to calculate the heat of neutralization. 150 ml of 0.5 normal nitric acid solution at 25.35 degrees Celsius was mixed with 150 ml of 0.5 normal sodium hydroxide solution at the same temperature. The final temperature was recorded to be 28.77 degrees Celsius. Calculate the heat of neutralization of nitric acid with sodium hydroxide. Now total mass of the solution will be equal to 150 plus 150, which is equal to 300 grams. Q is equal to total heat produced. So Q will be equal to 300 multiplied by delta T multiplied by specific heat of water, which is equal to 1 calories. Therefore, Q will be equal to 300 multiplied by 3.42 equal to 1026 calories. Now the heat of neutralization will be equal to Q upon 150 multiplied by 1000 multiplied by 1 upon 0.5, which is equal to 1026 divided by 150 multiplied by 1000 multiplied by 1 upon 0.5, which is equal to 13.68 kilocalories. As this is the heat liberated, hence heat of neutralization will be equal to minus 13.68 kilocalories. Sometimes the temperature of acid and base initially are not similar and water equivalent is also given in the problem. You can also calculate heat of neutralization in that case. Here is an example to show that. 100 centimeter cube of 0.5 normal HCl solution at 299.95 Kelvin were mixed with 100 centimeter cube 0.5 normal NaOH solution at 299.75 Kelvin in a thermos flask. The final temperature was found to be 302.65 Kelvin. Calculate the enthalpy of neutralization of HCl. Water equivalent of thermos flask is 44 grams. In this problem, the initial temperature of acid and base are not equal. Hence, initial average temperature of acid and base has to be calculated, which is equal to 299.95 plus 299.75 divided by 2, which is equal to 299.85 Kelvin. Therefore, rise in temperature will be equal to 302.65 minus 299.85, which is equal to 2.80 Kelvin. Hence, heat evolved during neutralization will be equal to total mass of the solution plus water equivalent multiplied by specific heat of the solution multiplied by delta T. This will be equal to 100 plus 100 plus 144 multiplied by 4.184 multiplied by 2.8, which is equal to 2858.5 joules. Therefore, enthalpy of neutralization will be equal to minus 2858.5 divided by 100 multiplied by 1000 multiplied by 1 upon 0.5, which is equal to minus 57.17 kilojoules. Let us revise what we have learned today. We discussed some applications of enthalpy of combustion, calorific value of foods and fuels, enthalpy of solution or heat of solution, and enthalpy of neutralization or heat of neutralization. In the continuation, we will discuss enthalpy of physical changes in next lecture.